Okay, wonderful. Thank you. Yes, today I would like to share with you some results that we got recently while studying optically driven spin excitations in an antiferromagnet. In particular, we found that ultrafast damping torques may enable the very efficient manipulation of antiferromagnetic order in these materials. And before we get into the topic, let me start with some acknowledgements. So although I'm currently a postdoc in the group of Suyang Xu at Harvard University, the work that I'm going to present today was done during my PhD at ETH Zurich in Switzerland in the group of Manfred Fiebig in a very close collaboration with Takuya Sato from the Tokyo Institute of Technology. And okay, if we now get into the topic and think about modern memories, the vast majority of all data is still stored as a magnetic bit somewhere where regions of oppositely oriented magnetization encode the logical zeros and ones. And okay, we can switch a magnetic bit very easily by applying a magnetic field. And unfortunately, this process is neither particularly fast nor particularly energy efficient, so that with our ever increasing hunger for more and more data, we expect a basically exponential growth of energy consumption, basically for, in this case, only for data centers around the globe. And the prediction here is that already in the very near future, this consumes a significant fraction of the overall global energy demand. That's a bit unsustainable. So the overall challenge here in general for information technology is to store and process data with the smallest possible amount of energy and at the fastest possible timescales. And recently, in particular for this workshop, the antiferromagnets emerge as one class of materials that may help to overcome these challenges. And in this talk, we're going to look at one specific antiferromagnet, hexagonal holmium manganite. But most of the results could be transferred to any other fully compensated antiferromagnetic system. Okay, holmium manganite, it has a hexagonal crystal structure, and the magnetic properties come from the manganese ions, which form trigonal planes in the crystal structure that are coupled antiferromagnetically, and then there are, along the C-axis, these planes are stacked. And the material orders antiferromagnetically at about 72 Kelvin and has a spin reorientation transition at about 33 Kelvin. And in this intermediate range, the spins assume a 3 clockwise, 3 counterclockwise spin orientation between neighboring layers. So the full dots here are one layer, the empty dots, the circles are the next layer. And at low temperatures, the spins assume the 3 in, 3 out kind of spin configuration that is shown on the left-hand side, actually, in this 3D illustration. And one approximation that we are going to make here already is the exchange interaction between two neighboring layers is actually quite weak. So we are going to neglect that. And we are going to consider the material as a triangular antiferromagnet with just 3 spins in the unit cell. And as there are 3 magnetic sublattices, the material has 3 Magnum modes that are commonly known as X, Y, and Z mode. And they're characterized by an oscillating net magnetization along the X, Y, or Z direction, respectively, during the spin precession. And among those 3 modes, we are going to look in particular at the Z mode precession. That is the mode that preserves the 3-fold rotational symmetry of the lattice. It has an oscillating net magnetization along the Z-axis. And yeah, this 3 spins always have the same Z component of the spins. And this mode is present in both phases, which also makes it very nice to use that for experiments. Okay, to study now what we can do with the material on the ultrafast timescale, we put the material into a pump probe setup. It's a rather conventional magneto-optical 2-color pump probe setup. So we use near-infrared pulses. The oscillating net magnetization along the Z-axis in our experimental geometry is out of plane. So we can simply use the Faraday effect to probe the magnetization dynamics, in this case with the Wollaston prism and the balanced photodiode. We induce the dynamics also with a near-infrared laser pulse. All pulses are around 130 femtoseconds. And as the excitation mechanism, we rely here on the inverse Faraday effect as a non-thermal excitation mechanism, whereby circularly polarized light in the material acts as an effective magnetic field, as explained in the introduction. Okay, what we can then do to determine how this field acts on the material is to plug it into the Landau-Schitz-Gilbert equation, apply another approximation, that is to ignore the damping term. The reasoning here is that this torque scales with the Gilbert damping parameter alpha, and in particular for antiferromagnetic insulators, alpha is usually much smaller than 1. Therefore, the second term is in magnitude much smaller than the first term. And if you then only consider excitation with the field torque, with the first one, we basically get an in-plane canting of all spins. And then during the spin precession, a net magnetization will appear as time progresses. Okay, the numbers work out in quite nice way, actually, that the 1 Tesla pulse for 100 femtoseconds can the spins by 1 degree. That's largely material independent, actually. Okay, this is a typical measurement. So we see a large signal at the time of the temporal overlap. And then at positive times, after the excitation, we see a damped sinusoidal signal that reflects the spin precession in the material. Good. We can then go ahead and fit this signal with a damped sine wave, sine function, and from that extract the frequency and the lifetime of the spin precession. And we did such measurements now for a range of temperatures that covered, in particular, the spin reorientation transition in holmium manganese. So let's have a closer look what we can actually learn from this. We get, first of all, the black data points. The black points are the data, and we see a clear dip of the frequency right at the spin orientation transition. We can model this behavior with a relatively simple, intuitive free energy expansion that has a nearest neighbor exchange interaction. It has some easy plane anisotropy that confines the spin to the XY plane. There's a weak in-plane anisotropy that actually determines then the easy axis of the spins. And we added here a also weak fourth order anisotropy that becomes important at the temperature of the spin reorientation transition. We further assumed, to make this a bit more accessible, that the in-plane chain anisotropy will just have a linear temperature dependence that crosses 0 right at the spin reorientation transition. So that favors exactly the two magnetic phases above and below the spin reorientation. Okay, looking into literature, we find the values for the exchange interaction and the out-of-plane anisotropy. Those were obtained by neutron scattering. And neutron scattering actually doesn't even consider those weaker anisotropy terms, because to fit the wide magnon bands that they see with neutrons, these effects have barely any effect. But in our measurements, we can now fit this model to our data and reveal these parameters, basically the kappa, the temperature coefficient, and the delta. And they are indeed on the micro eV scale, which is much, much smaller than what the neutron people see for their coupling constants. So those are just small corrections to the free energy expansion. However, I would like to point out that those corrections are technologically highly relevant, because it is, if you want, the weakest anisotropy that determines the thermal stability of a bit in a memory, for instance. If you have thermal fluctuations, as soon as they can overcome the weakest anisotropy, the bit is not stable anymore. And if you now look at a typical bit volume that corresponds in our case to about 500,000 spins, it's about 1 eV per bit, this barrier that we would need to overcome the anisotropy. So that's reasonably stable. This same energy barrier is also kind of the minimum you would need to overcome if you want to, in a precessional way, rotate all spins by 180 degrees. So it's a minimum energy to switch. And 1 eV per bit is it's kind of, well, it's significantly better than what we are doing right now. But it's a very idealized way to look at it, of course. Okay, having now the free energy expansion, we can go a bit further and try to learn something about the microscopic dynamics of these spins. So antiferromagnetic spin dynamics are always strongly elliptical because of the competition, basically, of a very strong exchange interaction and a relatively weak anisotropy. And we can define an aspect ratio of this elliptical spin precession as the ratio of the long versus the short axis of the ellipse. This geometric factor is sometimes also called the exchange enhancement factor. And knowing now the free energy and all the terms, we can basically calculate how that one would look in our material. And it peaks at the spin orientation transition as expected and falls a bit off. in both directions, and it is indeed significantly larger than 1, as we would expect for an antiferromagnet. Great. Now, with that in mind, let's see what else we can learn actually from our time-resolved measurements. So another parameter we can extract is the relaxation time, the time constant. And also that has some temperature dependence, of course. And what can we do with that? Well, if we solve the Untitled-Chapter equation for the antiferromagnetic spin precession in the material, we realize that actually the Gilbert damping parameter alpha never occurs by itself, but it's always the product of this spin ellipticity and alpha. So if you measure then frequency and lifetime in an experiment, you can combine those two to extract at least this A alpha product that should always work. Now, since we already have the ellipticity of our spin precession, we can then simply divide those two by each other and extract the actual Gilbert damping parameter in the material, which is, again, as expected, much smaller than 1. Good. However, if we also note that the dissipation and actually all physical properties are determined always by this A alpha product, we note that this value is around 1, which is not potentially a small number. So in that sense, maybe we should at this point reconsider an approximation we did earlier. We consider the excitation mechanism, where in particular we so far neglected the damping term and just considered the field-like torque for the excitation. Now, what would happen if we were to include this ultra-fast damping torque during the excitation? It would mean that the spins get canted also a little bit out of plane. And right after the excitation, there will be then a net magnetization. So there is a qualitative difference. In the experiment, this would show up as a change of the initial phase of the spin precession that we measured, the initial phase of this sinusoidal modulation. So in that sense, we can note that the Gilbert damping actually affects two things here. It's the lifetime of the spin precession after the excitation and the initial phase of the spin precession right at the moment of the excitation. Okay, let's see if we can see any signature of that. So we come back to our representative measurement, and now we can extrapolate the fit that we got here back to the time of the temporal overlap. And lo and behold, there is an initial phase. It does not cross 0 at t equals 0. Or another way to read this plot is to say that, okay, at t equals 0, there is a finite magnetization, a finite Faraday rotation, at least. Okay, now this is just a single measurement, and to be fair, yes, the initial phase is not very large, but we have this now for a range of temperatures, not just for one data point. And we can see if we see a temperature dependence of this initial phase. This is shown as the black dots here. By the way, in this blue shaded area, the Holmier moments start to order in the field of the manganese ions. So then that changes the free energy in a way that is not contained in our model. It can be included, but we didn't do that. So we're going to neglect anything that happens in the blue shaded area. And we find that there is a quantitative agreement in the area of interest, in particular around the spin orientation transition. Right, quantitative agreement between what? Well, we use this A alpha product here. If you solve the Landau-Schütz-Gilbert equation, you can show that the initial phase should be a function of this A alpha product. So using frequency and lifetime from the measurement after the excitation, we can extract this product and then plug it back into the calculative equation we find for the initial phase, and thereby determine what would be the expected initial phase if this damping torque of the inverse Faraday effect was present. And we find a quantitative agreement. Good, very good indeed. So the quantitative agreement shows that this damping torque of the inverse Faraday effect is in fact present in our material. And there is a second conclusion, that also, since we have quantitative agreement, the damping that is active after the excitation, the damping that is responsible for the finite lifetime of the spin precession, is the same damping that is also active right during the excitation. And this is not necessarily a given, as the spins actually move in slightly different ways during the excitation and during the relaxation. But it's potentially an interesting observation. Okay, so what is also interesting is that right, yes. So what's also interesting is that the alpha is still much smaller than 1, meaning the damping torque in magnitude is actually small. So the question could now be, why do we get from such a small torque an important measurable effect in our signal? And the reason here is that the damping torque and the field torque act in different ways. If we consider the energy of the spin precession after the excitation, it can be brought into such a form, basically. And the field torque of the inverse Faraday effect cannot induce a net magnetization. It can only rotate the antiferromagnetic vector. And rotating the antiferromagnetic order, it competes a bit with anisotropy in the material, which is a relatively weak energy scale. At the same time, the damping torque induces a net magnetization in an otherwise antiferromagnetic material, meaning that it frustrates the exchange interaction, which is a much larger energy scale. So then, even though the damping torque in magnitude may be smaller, its effect on in terms of energy transfer into the magnetic system is a lot more significant. So this gives actually damping torques in antiferromagnets in some sense a giant efficiency. And we can quantify this a little bit further if we when we note that actually the tangents of the initial phase that we plot here has a physical meaning. It's not just a measurement quantity, but it corresponds to an energy ratio of how much energy is transferred into the magnetic system by a spin excitation by the damping torque over how much energy is transferred by spin excitation via the field torque. So that means that if we enter a regime where the tangents of the initial phase is larger than 1, we enter the regime where the damping torque actually dominates the spin excitation mechanism. It results in the larger energy transfer. So in that sense, the initial approximation to neglect this damping torque during for the excitation process is maybe not necessarily justified. And with this, I would already like to summarize my talk. I hope I could show you that studying spin excitations in antiferromagnets is interesting in that it provides some valuable insights into the magnetic low energy landscape. In this case, we managed to quantify the weak in-plane anisotropy in hexagonal holmium magnetite, actually to my knowledge for the first time. And these informations are in principle relevant for also for applications. Then I further emphasize that the initial phase of an optically driven excitation encodes information about the excitation mechanism. That is also actually quite general statement. And in this case, we use the initial phase to show the existence of an ultrafast damping torque of the inverse Faraday effect. And lastly, basically the point of this talk was not only to show this damping torque, but to emphasize, to reiterate that exchange enhancement actually drastically boosts the efficiency of any mechanism that induces a net magnetization in an antiferromagnet. So even if it's not necessarily based on spin damping, as in this case, if any mechanism that manages to induce a net magnetization in an antiferromagnet will be highly efficient to switch the antiferromagnetic order, or at least induce larger angular spin precessions. And with this, I would like to thank you for your attention.